Okay, welcome here to lecture. I think we just have like one or two maybe slides to kind of finish up on gases, and then we will roll into solutions, which is the next chapter. So let's get a couple of things here out of the way. Okay, so we've been talking about gases, and obviously we've seen a number of gas laws that we talked about last couple of times here. We do have Boyle's law, which dealt with pressure and volume relationships. So P1 V1 equals P2 V2. This again is at constant temperature. We also saw, and again, in sort of that relationship as one goes up, one goes down, so they kind of go opposite of each other. We also saw Charles' law, which is V1 over T1 equals V2 over T2. This is at constant pressure. Remember this gas law and pretty much every single gas law that you have any type of temperature happening, it does need to be in Kelvin when you use it in the gas law. And again, as one goes up here, the other one also goes up. So as the temperature goes up, so is the volume, and that's really how it keeps the constant pressure happening, as we talked about last time. We also have Guy-Lussac's law, which is very similar. P1 T1 equals P2 T2. This is at constant volume. So unlike Charles' law here, we don't have that adjustment in the volume. And as a result of that, we do see basically as the pressure goes up, so does the temperature, and vice versa. As they both go down, so do they. They both also go down. And again, that's because as the temperature increases, gas molecules are moving faster. Faster moving gas molecules mean more collisions. More collisions mean more pressure. We talked about Avogadro. V1 N1 is equal to V2 N2. This is at two conditions that are constant. This is constant temperature and pressure. And basically as the moles of the gas, which is what N is the moles of the gas. The number of moles of a gas as it sort of increases, so does the volume sort of proportionally. You kind of take all these guys together and we get that ideal gas law that we talked about, which is PV is equal to nRT. Remember, really out of all these gas laws, obviously all these temperatures here need to be Kelvin as well. This is the most restrictive in terms of the units, and it is also sort of a one condition type of deal, which means you have one pressure, one temperature, unlike the ones above where you have kind of twos of everything. Pressure here does need to be in atmospheres. Volume does need to be in liters when you use the ideal gas law, and should hopefully be moles. And T, like every other gas law, does need to be in Kelvin. And the reason for all that is R, which is the gas constant. And again, that's a value that you always have, 0.08206 liters times atmosphere, Kelvin times mole. So a reminder that, you will probably have this number given to you with the units. So that's a helpful way to remember what everybody else's units basically need to be when you use this. We also saw a couple other terms like STP. STP is standard temperature and pressure. And when somebody says at STP or this is under STP conditions, they're actually giving you values for temperature and pressure. The temperature value would be 273 Kelvin if you needed to use it. And the pressure value would be 1 atmosphere. So again, if they say STP, it actually are two sort of values that you could use, obviously in an equation, in a calculation, and so forth. There is a sort of special relationship that we also talked about that occurs at STP and STP conditions only. So if you happen to find yourself under these two conditions here, and it has to be both those conditions, any gas, 1 mole of any ideal gas, will have a volume of 22.414 liters. And that's a sort of shortcut, if you will, that would allow you perhaps not to have to use the ideal gas law. But again, it does definitely has to be at STP conditions. So if it's not STP conditions, you for sure need to use the ideal gas law. If it is at STP conditions, you have a choice. You could either use the ideal gas law by putting in 273 for the temperature, 1 atmosphere for the pressure, or you could use this kind of conversion. I think we finished up last time, actually, with a couple of other ones we added to the list here. We had the combined gas law, which was P1 V1 over T1 is equal to P2 V2 over T2. So this is sort of a situation where perhaps we have all three of the sort of variables in play, and maybe one of the three is changing, or a couple of them are changing, actually. We can see what happens with that. We also talked about, the importance of being able to rearrange these equations properly. So a reminder that, sort of the quick way to rearrange, if that's the equal sign in the middle and you got something up on top, it goes to the opposite side, and obviously vice versa. So sort of the crossover move. So if you're moving any of these variables to the other side, they should always end up in the opposite location of where they started as you cross over the equal sign. We finished up talking last time about the idea of partial pressures. And partial pressures basically occur as a result of a mixture of gases. And basically here, when you have multiple gases that are flying around in the same container, the total pressure is really equal to the pressure of all those gases, however many gases you may have. We'll just say we have 3 gases, for example, A, B, and Z. The partial pressures of each of these gases, that's what the P's would stand for here, added together. How do you calculate the partial pressures? There's several different ways that we sort of solve. Most common way is just to use the ideal gas law and basically just solve for P. And what you would do is sort of what we talked about last time, that the idea of an ideal gas is one of the things is we don't really think about it as sort of interacting with other gas molecules that may be in the same container, which means we basically can do the ideal gas law here 3 separate times, one for each of the gases that would be present. And the nice things also about this is because they are in the same container, the volume for all the gases will be the same. And the temperature, because that container is really sitting in the same spot, will also be the same for all the gases. And what that really means, if temperature is the same for everybody, volume is the same for everybody, R is a constant. Really, when you're doing partial pressure problems, the one thing that you just need to figure out is basically the moles, which may be given to you in moles, may be given to you in grams, that you can convert to moles using the molar mass from the periodic table to do so, which are grams per mole, the periodic table. Again, as discussed in those chapter 7 lectures and what we talked about during discussion as well last week. Another very common sort of partial pressure situation is a result of how gases are collected. So sometimes if gases are sort of collected in a very bad drawing here, we'll call that just a hose. So if we're collecting this gas here with water, we oftentimes will collect in that empty spot the gas we're interested in, plus what is referred to as water vapor. And that means that the total pressure in that case would be the partial pressure of the gas we're interested in, plus the vapor pressure of water, which you can look up in a table. And this is one of those subtraction type deals. So the pressure of the gas we're interested in would be the total pressure minus the vapor pressure of water. These two guys is the vapor pressure of water. And again, it's sort of a subtraction sort of situation. Any questions on any of that stuff from gases that we talked about the last couple of times, I think?
Sir?
Yeah.
I just have a quick question. I know we have all these gas laws like Boyle, Charles, and the whatnot. I was just wondering if when we do our exam, are we going to have these at our disposal, or is it our job to remember it?
You will need to know most of these. I think it will say on the review sheet. I'm trying to think. I think you might be given the ideal gas law, but you should know probably most of these. And that's a good question. I want to just show you also, a way that you could kind of get yourself to each of these gas laws without perhaps a lot of memorization. If I were to choose, with all these guys up on top, for example, all these sort of gas laws here, for the most part, I would go with this guy and sort of focus in on that guy. And that's because, for example, let's see if I can find somewhere I can scribble. I'll scribble over here. So if we look at that sort of combined gas law, which is the P1 V1 over T1 is equal to P2 V2 over T2. From this gas law, you could pretty much get Charles, Boyle's law, the Guy-Lussac's law. So for example, if we were given a problem where, you were just given pressure and volume, but you weren't given any temperatures, or it said temperature was held constant, you could just basically cross that off. And then what's left over would be Boyle's law. If you had a problem where, you were given volumes and temperatures, but no pressures, you could scratch out the pressures here. And now you basically have Charles' law. If you were given a problem where you had pressures and temperatures given to you, but no volumes, again, you could cross out volumes, and then obviously you would have Guy-Lussac's law. If you remember this guy, you will then have the combined gas law also obviously memorized. And from now on, you could get everybody, which will kind of just leave you mostly PV equals nRT to remember. So this is a really good one to remember. And really from that gas law, you can get yourself to any of the other gas laws that you would need to get by really just scratching out whatever was not given to you in the problem. And that's a really good way to kind of get yourself to all those without maybe just separately memorizing them all. Just know that one, scratch out what you're not given, and you'll have really the gas law that you need. Other questions on that? Okay, so that's again a really good way to kind of get yourself to those gas laws. And then really at that point, you probably would be only these two that you would really need to concern yourself with, as you could get to the other ones really from the guy on the left there. Any questions on how to do that there? Okay. So to finish up sort of the gas chapter here, we talked about some of this stuff here, but let's talk about the kinetic molecular theory of gases. And the kinetic molecular theory of gases basically describes a lot of things that we talked about along the way here. Gases are obviously tiny particles, atoms or molecules. They're obviously in motion, and as they fly around, and they cause those collisions, this is what we associate with the pressure. They are small compared to basically the distances between them, and the volume of the actual gas molecules is thought to be basically negligible or zero compared to basically the container that it's in. So if you think about a lot of sort of problems that we've done or seen, or a lot that you maybe will see, online or in the book, a lot of times they talk about the volume more of the container that the gas is in, as we assumed as being filled uniformly, rather than the actual gas itself and its volume. And that's really one thing that makes something, we call it an ideal gas. That's really one thing that makes something an ideal gas, that, the volume of the container itself is much larger than the actual gas molecules themselves. So we're more interested sort of in the volume of the container rather than the actual volume of the gas. As they are obviously in random motion, they're colliding with the walls of the container. That is really what is causing the pressure we associate with gases. Obviously, the more collisions, the higher the pressure we would assume. The less collisions, less pressure we would assume. And number 4 is really the other part of this theory that makes something an ideal gas. And it's a belief that the particles are assumed not to really attract one another or repel one another. And that's really why what we were just talking about there in terms of partial pressures, why we could have a mixture of gases where they're all in the same container. And basically, we could treat each gas individually like they were in there by themselves. As in an ideal situation, there's really going to be kind of no interaction happening between the different gas molecules. So really number 2 on this list here, and number 4 on this list is really what makes something an ideal gas, which is what we deal with in this class, as opposed to a real gas, which we don't really talk about in this class, which don't basically behave like this. And the average kinetic energy of gas particles is directly proportional to the Kelvin temperature. So like what we saw with Charles' law, as the temperature increases, we do see the gas molecules moving faster, which usually will result in sort of multiple collisions. So a couple of key points that we saw in some of those relationships that we talked about. Temperature is a measure of the motions of the gas. Again, higher temperature, gas molecules traveling faster, hitting the wall more often. Again, if the volume does not move, we would expect the pressure to increase in that case. Lower temperatures, they're not moving as fast, so they're flying around slower. Going to take longer for those collisions basically to occur. And again, as a result, if the volume does not change, we would expect the pressure to start to drop. In a rigid containers, that's really what we're talking about there in the middle. Without that volume adjusting, as we talked about last time, if really the volume does not adjust, if we have a really high temperature, gas molecules flying around a lot faster, more collisions. Again, if they are lower temperature, they're moving around a lot slower, a lot less collisions basically happening. And again, the difference in pressure would obviously be seen. Here we would expect the pressure to go up. Here we would expect the pressure basically to go down. Volume and temperature, again, the way it's able to keep the pressure from going up and down is in a Charles law situation. We do get sort of a movable sort of volume, where if we increase the temperature and things are moving faster, we will see the volume also increase. And what that basically is able to do is keep the number of collisions relatively constant to each other. And that would also keep the pressure constant, and vice versa. If it gets really lower in the temperature, basically the volume is going to crush down on those gas molecules. And even though they're moving a lot slower, it will still keep the rate of collisions happening at the same rate, and thus keep the pressure constant. Any questions on any of those sort of gas laws, relationships that we talked about? Okay, so that does wrap up, I believe, chapter 8, which is the gases. So we will then move on to chapter 9, which is solutions. So let's get that going here. Okay, so in this chapter, obviously, we're going to talk about solutions. We're going to talk about concentrations, some different aspects of solutions. And again, let us talk about really some differences in terminology and some questions that sometimes people have in regards to solutions. What is a solution? How do we know it's a solution? What makes up an actual solution? Well, first off, one way that we could recognize that something is a solution is actually in the formula. A lot of times we will see this symbol next to it, which is the AQ or aqueous symbol. and that is aqueous. And remember that the aqueous symbol is different than the liquid symbol, which is the L. A liquid symbol is a pure liquid, again, like nothing else there. Like if you just had pure water by itself, that would be a pure liquid. If you took something like pure water and you took some solid sodium chloride and you dissolved it in pure water, you will then make a sodium chloride solution that would get the aqueous symbol next to it. And what does that mean? It means that basically all the sodium chloride would have dissolved in the water, and you now have basically something that looks like water, but has sodium ions and chloride ions floating around. And again, you don't have that with water. It's just H2O molecules basically in that solution. Now, a solution is a homogeneous mixture. So as we talked about with mixtures, homogeneous means everything dissolves, everything looks the same throughout. And there are actually two parts that make up the solution. And the first part is the smaller part of the solution, which is the solute. And the larger part of the solution is the solvent. So the solute is the smaller part, and the solvent is the larger part. And basically in our example up here, when we make our sodium chloride solution, the water here would be the larger part, right? If you took some salt and you dissolved it in water, that would be our solvent. And the sodium chloride here, which is what was dissolved in the solvent, would be the solute. So that is both of those things together make up a solution. How do you know which one's which, or how do you know the name of the solute? The good news is the actual name of the solution or the formula of the solution is always the solute. So if you say you have a sodium chloride solution like we have here, that means that sodium chloride would be the solute. If you had a silver nitrate solution, that would mean that silver nitrate would be the solute. Most of the time, and again, not 100% of the time, but most of the time, the solvent will be water. But water, as we'll talk about in this chapter, may not always be the best thing to use as a solvent. But in a lot of aqueous solutions, a lot of solutions that are really ionic solutions like sodium chloride, silver nitrate, potassium chloride, things of those natures. A lot of times water is a very, very good solvent. But again, sometimes people get into the mindset that water is 100% always the solvent, and it's not. So you could use other things as solvents. And like I said, sometimes water is actually a pretty bad solvent. You wouldn't want to use water in certain situations. And we'll talk about some of those situations, obviously, in this chapter. Here's sort of that process there. We have our solution here of water and some copper 2 sulfate. The water, which is the larger part, is our solvent. The copper 2 sulfate here is our solute. And in this case, as we mix it, as you can see, larger part, smaller part, we give it a mixy here, shaky, maybe not so much shaky. And basically we're going to get all these guys to basically dissolve. And in this solution, again, looks the same throughout. We don't see any solid, all looks like one layer. And that would be an aqueous solution of copper 2 sulfate. So, if we were to call what this solution is, it would be a copper 2 sulfate solution. The copper 2 sulfate, which is the name of the solution, would tell us that is the solute that we are dealing with. Any questions on that there? Now, how does things sort of dissolve in water, for example? As I mentioned, water is a really good solvent for a lot of things. Water is a really good solvent for things that are polar. Water is a very good solvent for things that are ionic. And that is because when you think about water and you think about sort of Lewis structures and all that stuff that we talked about with bonding, if you draw water, water is actually a polar molecule, which basically, if it's a polar molecule, that means there's a side of water, for example, that's more negative, which is actually the oxygen side. And there's a side of water that's more positive, which is actually the hydrogen side. And that is because, as we talked about with bonding, overall, there is unequal sharing of electrons here as a whole. And the electrons are hanging out near the oxygen side more than they are near the hydrogen side. And it creates, again, a side that's more positive, more negative. So why would that be good for things that are ionic? Why would that be good for things that are polar? It is good because when you take something like sodium chloride that's solid and you throw it into water, it breaks apart into sodium ions and chloride ions. And in chemistry, as we talked a lot about up to this point, there's that idea of opposites attract. And basically what will happen is the water will go cool. I'm going to come over here to this ion that's positively charged, and basically a bunch of water molecules will kind of surround it. And it would surround it by the oxygen. And that's because the oxygen is more negative in water. So we have that kind of negative, positive attraction that occurs. The same thing will happen with the chloride. We'll get some water molecules that will come in and go, cool, chloride, negatively charged. And some water molecules will actually surround the chloride. But it surrounds it differently than it does the positive guy. It surrounds it with its hydrogen part. And that is because hydrogen is more positive than oxygen. So the positive part of water would be attracted to the negative guy. The negative part of water, which is the oxygen, is attracted to the positive guy. And now what happens when you visually look at it is you visually look at it and go, the sodium chloride disappeared. It's gone. And the reason that this is actually a physical change is because the sodium chloride isn't really gone. It has just basically got surrounded by so many waters, the ions, that we can't really see it anymore. It's still there because maybe you did this experiment or will do this experiment. If I decided to take this guy and heat it up, it's a wonderful arrow fire there that I just drew, and I start heating this solution here of basically sodium chloride. When I heat something that has water, what happens is the water will start to evaporate. So we will start basically evaporating off all these waters. And now when we get all these waters out of the way, by heating this up and evaporating it, there's absolutely nothing preventing these two guys from coming back together, which they definitely want to do because there's a very strong attraction between these two ions. These guys will then come back together. And if you did this like in a dish, what you would see is probably not a red residue, probably be a white residue if it's sodium chloride, but you would see the solid come back. And that's basically your physical change, right? You don't really change fundamentally what it is, but it may look different. And even though you can't physically see the salt in that salt water, it's actually still there. It just got surrounded by all these waters that basically pluck it off. When we go to dissolve something like sodium chloride in water, what do we typically do if it's a solid in a liquid? We stir it, right? And when we stir it, basically what that's doing is throwing a bunch of water molecules on the solid sodium chloride. That's going to allow those water molecules really to pluck off each of those ions, and also is going to provide a lot of energy for needing that, right? That's why when you just pour a solid in, you just let it sit there, it would take a while for it to dissolve rather than going a little bit quicker if you kind of stir it up or mix it up. Again, you're sort of helping the process by splattering a lot of water around those ions. Any questions on that? Here's probably a much better picture here. Again, with your solid in your water, all these water molecules come in. Again, they start plucking off these ions. And again, they start to surround the ions. And again, the positive ion is surrounded by the negative side of water. The positive side of water surrounds the negative guy. And again, by stirring it, like I said, you're throwing a lot of water molecules on the solid. This, by the way, here is the solid before it dissolves, the kind of organization of positive, negative ions together. And that again helps the process of it to dissolve. Same thing here, in case you like this picture better, as it kind of plucks them off. And third picture, in case you didn't like the first two, here's the same idea. Clearly here, we need to help this along by stirring this, again, getting a lot more water molecules all over that surface, helping them to start plucking off these ions. And again, this is the solid here. And this is what ionic solids look like. They arrange themselves in this kind of pattern where the positive and negative guys kind of sandwich themselves in together. So let's talk a little bit about solubility in water. And there are certain things that are soluble in water, and there's certain things that are not so soluble in water. But we'll start with the stuff that is soluble in water. Anything that's ionic, like I mentioned before, things like sodium chloride, ammonium nitrate, ionic things are definitely soluble in water for that reason. In water, they break apart into ions. And again, they all get surrounded by the water, either the positive side or negative side. But there's also some ionic compounds that are non-ionic compounds that are also very soluble in water, things like sugar, things like ethanol. So why is something like sugar or ethanol sort of also soluble in water? If I draw something like ethanol here, we'll borrow the yellowness here that's pre on the page. This is ethanol, for example. And ethanol kind of has two parts. It has this part here that's all carbons and hydrogens. And as you remember from bonding, hopefully carbon and hydrogen are non-polar bonds. So that's really non-polar. Remember, if something's non-polar, one way you could kind of look at it is it's kind of neutral. There's really no charge. There's not a side that's positive. There's not a side that's negative. But the one thing that something like ethanol, for example, does have is what's in the green part there. In the green part, there is this OH bond. And again, if you think about bonding like we talked about, this OH bond is a polar bond. So it has this little polar bond where the oxygen is more negative, hydrogen is more positive. And it's actually that little piece of something like ethanol that allows it to interact really well with water. And that again is because the oxygen is negative here in water, hydrogen is positive. So opposites attract. The oxygen from one will be attracted to the hydrogen in the other. This creates, as we'll talk about, what is referred to as a hydrogen bonding. And it allows something like ethanol to be very, very soluble in water because it has this small part. As we'll talk about, this is kind of an organic molecule, as we'll talk about in organic chapters, the solubility decreases a lot if this size gets larger. So if you have something with a lot of carbons and hydrogens, the solubility goes way down because you have this really big thing that's pretty much nonpolar and just a small little part that's polar. And it doesn't allow really water to interact really well with it. But things where 6 or less carbons in a lot of cases that has an OH group on it is able to interact really well with water and be soluble. Sugar, what's the deal with sugar? Well, sugar is a little bit larger of a molecule, but it pretty much is littered with OH groups all over it. So everywhere there's an OH group on something like sugar, it allows it a place to interact well with water and makes it quite soluble. So if something is soluble, we oftentimes will use a couple of different words. So soluble means usually that, you know, if it's a solid, it will dissolve in a liquid like water. If it's insoluble, it means typically that it will not dissolve, and you would expect like a precipitate or a solid to form. Sometimes when we talk about liquids, if we're just talking about two liquids in each other, if two liquids mix really well with each other, that's what is sometimes referred to as being miscible. Same thing as being soluble. It all looks like one layer. if we have two liquids that we put together and they really are insoluble in each other, we will see different layers. So we'll see these kind of different layerings that will happen. And that is sometimes referred to when you're talking kind of liquid on liquid as being immiscible. And again, that's basically the same thing as insoluble. So sometimes people use insoluble and soluble for describing what happens when you take a solid into a liquid. Will it dissolve? Will it not dissolve? Sometimes people will use miscible and immiscible if you're talking about just two liquids kind of coming together. Will they mix or not mix? Any questions on that there? Basic interactions for things that allow things to be soluble in each other means that they do have to have very similar sort of interactions in order to really kind of mix and really be soluble in each other. And most interactions that occur between molecules and molecules is the basic positive negative electrostatic attraction. This is the basic what is sometimes referred to as intermolecular forces, the forces that hold one molecule together with another. So here's methanol, also has that OH group, which is negative and positive, allows the negative oxygen to bond with the positive hydrogen in one, positive hydrogen in the other, allowed to bond with the negative oxygen in another, and again, makes it very soluble. Here's a prettier picture of the ethanol that I drew earlier. So what happens when we kind of get things that maybe don't mix so well? So if we take some oil and put it in water, those two guys pretty much don't mix well at all. And they don't mix well at all because what makes up oil is really insoluble, I guess is a better word or way of doing that, insoluble in water. And that's because pretty much what makes up oil is nothing but a long chain of carbons attached to carbons. I'll just draw a few here, but it just continues. And basically attached to these carbons are hydrogens. And a couple of things about polarity here of all these guys. The carbon hydrogen bond, as we talked about there previously, is a non-polar bond, which means, again, equal sharing of electrons, no positive side, no negative side. And clearly the bond between the carbon and carbon would also be non-polar. And that means when a water comes by, water here has a negative side and a positive side. It's looking for something like that to interact with oil, and it doesn't have anything. Again, you can think of oil as sort of being like neutral, if you will. So it doesn't have a long way to interact with one another. So they cannot really interact very well with each other because they have no way to do that. The water here is actually going to be trying to use something that is known as hydrogen bonding, like we talked about a second ago. The oil here is actually going to be using something known as dispersion forces. And they're going to have no real long way of interacting with one another because they have no way basically to maintain that. They can for a very short period of time, but they don't have a way to keep that interaction basically going. So they can't basically dissolve in one another or mix with one another. And that brings up a very important sort of way for these interactions to sort of happen. In order for something like oil, which is really big, has no way to interact well with water, in order for it basically to dissolve in water, is it's got to break apart basically these water interactions that are there. So before anything dissolves in water, there's just a bunch of water molecules that are basically bonded to each other. So in order for something to come in, it's got to basically break these bonds and kind of replace them with similar bonds. And that really doesn't happen in the case of water because it's so large. It's not really using the same type of bonding. And that brings up an idea of what is known as like dissolves like. And when we talk about sort of these interactions, let's see here real quick. 1 second. So when we talk about these interactions, we should talk a little bit about sort of the interactions that happen between different molecules. And I thought maybe we did, but just in case we didn't, let me just talk about that really quick here, just to illustrate that point. Where I want to go here, let's go here. So go right to the beginning there. We'll come back to this one. Go here. So let's talk a little bit about how sort of molecules interact with one another, just to make sure that we did cover it. When one molecule interacts with another, that is what is known as, again, intermolecular forces, just to remind everybody. I think it was in an earlier chapter, but just to make sure. So intermolecular forces are really the forces that hold basically one entire molecule together with another. So for example, if we're talking about one water molecule being bonded to another water molecule, it is that force that basically holds those two guys together. And that's an intermolecular force. That's different than if you took one individual water molecule, the actual OH bond on each side. That's what's referred to as an intramolecular force, which means within the molecule. Intermolecular forces are much weaker than intramolecular forces. That's because we know this: when we heat something like water, the very first bond that breaks is the bond between the two water molecules. So your liquid water goes from liquid water to steam, which is still water. So we break that bond between the two. If it was opposite and we heated it and the intramolecular forces were weaker, we would actually see hydrogen gas being developed and oxygen gas being developed, which obviously doesn't happen. Otherwise, again, you want to get to the pasta making of the evening. So intramolecular forces are always stronger. And these are, again, things like ionic bonding, covalent bonding, what we see within a molecule. So what we're talking about here in terms of solubility, it really does relate to intermolecular forces, the forces between different molecules. And there's really three types of intermolecular forces. There is what is referred to as a dipole interaction. And that happens with polar molecules. So this happens when a polar molecule interacts with another polar molecule. And remember, if it's polar, like we were just talking about, what that means is there's a side of the molecule that's more positive because of unequal sharing of electrons, and a side that's more negative. And that means that when two polar molecules come in contact with each other, are near each other, they're able to interact via the positive side of one and the negative side of the other. And that's what basically holds those together. There's a special type of dipole-dipole interaction, which is what is referred to as hydrogen bonding. And that is with polar molecules and polar molecules coming together. And you may be asking, so what is the difference between the two? The difference is in hydrogen bonding, we have a hydrogen that is bonded to either nitrogen, oxygen, or fluorine. And if you look on the periodic table, nitrogen, oxygen, and fluorine, remember electronegativity increases as you go this way, with fluorine being the most electronegative. That means when we take something, for example, like water, negative and positive, and another water molecule, negative and positive. The negative side of one is attracted to the hydrogen in the other. This is considered hydrogen bonding because when we look at the water, it is a bond between hydrogen and oxygen. And this guy, hydrogen and oxygen. So there's that bond that you need for it to be hydrogen bonding. If we had something like this guy, I'll draw all the electrons here, but we'll do this. This is also a polar molecule where the more negative side would be the fluorine side. More positive side here would be the carbon side. And if you have this guy with itself, we would have, kind of the positive side attracted to the negative side. And again, this would be dipole-dipole interaction, not hydrogen bonding. Although there is a hydrogen here, it is attached to carbon, not nitrogen, oxygen, and fluorine. And that illustrates a really good point that you could have a lot of hydrogens there, but it does need to be the correct type of hydrogen for it to interact this way. In this case, that hydrogen would not be able to do it. The last type of intermolecular force is dispersion forces. And these are really the weakest out of them all. And these are temporary forces. And these are basically how nonpolar molecules interact with other nonpolar molecules. So if we have two nonpolar molecules, I'll just write NP for nonpolar, they basically have no charge. But it is possible that electrons that are flying around, they may all decide, hey, we're just going to kind of go to this side of the molecule. And what will happen in this case is this nonpolar molecule, which normally does not have a charge, will temporarily gain a charge. And that means one side will become negative, one side will be positive. That also means that if it's still next to this other nonpolar guy, the electrons in this guy is going to go, cool, I want to go this way. I'm attracted to that positive guy. Now, the second guy, which also normally doesn't have a charge, will also temporarily gain a charge. And this now gives them that positive negative way to interact with each other. It's temporary because as soon as those electrons kind of move back or something else happens, it breaks apart and new ones form. So dispersion forces are pretty much your nonpolar interaction. Your dipole-dipole interaction is when two polar molecules come together that does not have the ability to hydrogen bond. And hydrogen bonding is also between polar and polar molecules that has the ability to hydrogen bond. The strongest interaction out of all these is hydrogen bonding is the strongest. The weakest out of all of them is dispersion forces. So strongest hydrogen bonding, weakest dispersion forces. And again, these are sort of the interactions that really do interact with solubility and why certain things mix really well and certain things don't mix really well. Any questions on the differences there? By the way, just an example here for this last guy, if he had CH4, that is a nonpolar molecule, even though it's got a ton of hydrogens. If you wanted it to interact with another CH4, it would be using dispersion forces. So again, even though there's a lot of hydrogens, it cannot hydrogen bond because the hydrogen is not directly attached to a nitrogen, oxygen, or fluorine. The reason that's important for hydrogen bonding is that will create a polar bond and that separation of charge that we need for that interaction to occur. Any questions on any of these guys here? Okay, then let's go back to what we were talking about now that I made sure that we talked about this. We're here, I think. So when we talk about like dissolves like, what we're really talking about is, things that have very similar intermolecular forces, things that interact with each other in a very similar way, are able to be soluble in each other. So when we talk about like dissolves like and solubility, typically things are soluble if you have a combination of something that is polar and polar, because they both will use hydrogen bonding, or they'll both use dipole-dipole interaction. They're able to interact really well. If you have something that is ionic and polar, those things also will mix, like we talked about with the sodium ions and the sodium chloride ions in the water. And if you have something actually that's non-polar and non-polar, they also will interact well with each other. Again, they're both going to be using that dispersion forces, which is that weak temporary way of interacting, and they would work really well. You run into trouble if you kind of cross over there. Things are insoluble if you take something that's polar and non-polar together, and those guys really will not interact really well with each other, because again, they don't have a long way to keep that interaction going. Sure, if you mix some like oil and water, right, it will mix for a second or so, and then eventually it will kind of separate out. And that's because it lacks that long-term way of keeping that interaction going. Any questions on that there? So here on top is sugar. And again, like I said, it's a little bit bigger of a molecule, but what we see in sugar is it's just loaded with OH groups all over, and everywhere there's an OH group, that's that polar group, and that allows everywhere pretty much water to interact with it, from the negative of the oxygen to the hydrogen through hydrogen bonding, and makes sugar really, really soluble, as opposed to down here is pretty much oil, again, non-polar, not going to interact really well. And typically what we see when we put oil in water is we do see this sort of separation out, where we have sort of the oil layer on top, the aqueous water layer on the bottom. Again, the water molecules and water molecules are all bonded to each other. In order for this big guy to interact, he's got to kind of bust through that and mix well with it. And again, because it really doesn't have that long-term way of doing that, it's really not going to be able to do that, again, because this guy up on top is non-polar. Water obviously is polar, and those two things, as you can see here, really don't mix. So when we talk about solubility, again, obviously if something is soluble, come back, if something is soluble, that basically means that one thing typically will dissolve in another. So like our water and sugar example, our water and salt example, they are soluble in each other. If one thing doesn't dissolve in another, like oil is insoluble in water, they really won't mix or dissolve. For example, if you were taking something like chlorine, just straight chlorine, which is a non-polar molecule, if you try to use water as a solvent, that's a really bad move, because you will get those guys not interacting with each other. The chlorine will actually be up on top and the water will be on the bottom, and you'll get this kind of separation. Now, if you take the chlorine and you put it in with some hexane, for example, which is basically 6 carbons with hydrogens all around, too close up there. Imagine there's a hydrogen up there on top all the way around. Badly draw it up there. It keeps getting in my way. Move it for a sec here. There you go. This guy is pretty much non-polar, and it will interact really well with the Cl2, which is non-polar. And again, this would be a case where water would not be the greatest solvent. Something like hexane would allow that Cl2 basically to mix with it. So again, water is good for a lot of things, but not always the best solvent, especially not a great solvent for things that are non-polar. You would want something that's non-polar for those guys. There's usually a limit to the solubility of one substance in another. You know, if you just take a ton of sugar, for example, and keep dumping it into a glass of water, at some point, you know, it will stop dissolving. There's only so much you could get to dissolve at a given temperature. It is temperature related. But there are things that are also soluble in each other all the time. Gases are soluble in one another, and that's because gases are flying around, which means by that they are constantly mixing with each other as they're passing each other. Some liquids are also soluble in each other. So polar and polar, non-polar and non-polar things are soluble in each other. Now you may be asking, you know, what happens if I mix a couple of things? How do I know if, you know, I am going to get perhaps a solid or maybe not a solid form? And one thing that helps us determine when we mix, especially ionic compounds together, are solutions that contain ions, whether or not we'll get something that's solid is this thing here. This is what is known as a solubility table. And a solubility table helps us determine whether or not, if we kind of throw together a couple of things, would we expect those ions to basically make a solid or not make a solid? And if we determine based on the table here that it is soluble, it would get the aqueous symbol next to it, which means we would not expect any type of solid to form. If we look at this table and we see something that is insoluble, we would expect a solid to form. So let's take a look at some of these rules here. Basically, anybody in group 1 on the periodic table, lithium, sodium, potassium, if you see that in an actual chemical formula, it is going to be soluble all the time. There's absolutely no exceptions, which means you're good to go. As soon as you see one of those guys in there, you can basically put the aqueous symbol next to it. You'll know it's going to be a solution. It's going to be soluble. Same thing with ammonium. If it has NH4 in the formula, it will be soluble. Again, there's no exception. Nitrates as well. If you see NO3 in a formula, it will be soluble 100% of the time, no exceptions. Now, if you see chloride, bromide, or iodine in a formula, it is typically soluble, but there are 3 exceptions. This is silver, lead, and mercury 1. So if you have like silver and chloride together or silver and bromide together, that is an exception. So normally things are soluble. The exception would be the opposite, which means if you have any of these 3 guys, they would then become insoluble and become a solid. Now there's sulfates, which are also soluble in everything, but here there are 4 exceptions. So again, if you had any of those 4 exceptions in a formula with sulfate, that means that it would be insoluble instead of soluble, and you would expect a solid. There are certain things that are insoluble. So carbonates, phosphates, and hydroxides, if you see any of these formulas in a chemical formula, they're going to be insoluble, which gets the S normally, as opposed to these guys that get the aqueous. But if there is group 1 or NH4 plus, which is the guys from above, they would then become soluble and be aqueous. If it's group 1 and NH4 with phosphate, they would also be soluble and aqueous. If it's group 1 with calcium, strontium, or barium and hydroxide, it would also be soluble. That is why when we have something like sodium hydroxide, it is hydroxide, which is normally insoluble or a solid, but sodium is involved, which is part of group 1. So it becomes the opposite, and this guy would be soluble and aqueous in this particular case. Any questions on that there? So let's see how we can use this. Let's say we looked at a double displacement reaction such as this silver nitrate plus some sodium chloride goes to silver chloride and sodium nitrate. Let's say we wanted to use this table to determine, you know, are these things aqueous, which means they're solutions? Are they solids? So we would look at each of the formulas and make that decision. Although we may not be able to see silver on the left-hand side, we do see nitrate. And nitrate's right here. which means it is soluble and there's no exceptions, which means as soon as I see that NO3, I know this is going to be soluble, is going to be aqueous, and it's going to be a solution, no solid involved there. So it's going to be a liquidish state, but it is a solution. That is the aqueous symbol. When I look over here, I see sodium, which is all I need here. That is group 1. It is soluble in everything, and there's no exception, which means that is all I need to do and look at to determine that this guy also should be a solution and aqueous. You could look at the chloride. It is chloride. It is also soluble, and it is not part silver, lead, or mercury here, so it's still going to tell you it's aqueous. When we look on the next side of the arrow, we got silver and chloride. Again, looking at chloride here, chloride is soluble in everything except for silver, lead, or mercury 1. In this particular case, our chloride is with silver, which means it's going to be the opposite of soluble and actually means that this guy is going to make a solid. And lastly, here we look at sodium nitrate. Sodium is as far as we need to look. It is group 1. It is soluble in everything. And that means that this would be aqueous. You could also look at the nitrate if you want. Nitrate, like we saw earlier, soluble in everything, no exceptions. So basically, when you would take this silver nitrate, which is a solution, and mix it with sodium chloride, it's a solution, you will get this white solid that would form. And that white solid that you would see, you would expect it to be the silver chloride based on these solubility rules. Question on how to use that.
Professor, will we have to memorize this
This
chart, or would it be available during a test?
This would be provided for you if you needed it. You just need to obviously know how to use it. Yeah.
Okay, thank you.
You're welcome. So why don't you try one here just to make sure. So let's take lead to nitrate plus some potassium iodide and goes to lead to iodide plus some potassium nitrate. All right, so take a minute or two here, use this table that I hopefully didn't scribble too badly on, and decide, for each of these sort of formulas, should they get the aqueous symbol, which means it's soluble and no solid is formed, or should they get the solid symbol, which obviously means a solid has been formed and they're insoluble. So take a second and see what you come up with. Okay, let's take a look and kind of see how we did here. So again, you may not be able to find both on the chart. You may or may not, but at least you should be able to find one. So looking here, I might not be able to find lead per se, but I can find NO3, which is nitrate. And again, nitrate is soluble in everything, and there is no exceptions, which means that's all I need to determine that this guy should be a solution and be aqueous. When I look at this one, which is potassium, potassium is part of group 1, and it's soluble in everything, and there's no exceptions. So really that's as far as I need to look. Because there's no exceptions, I would also know that that guy would be a solution and get the aqueous symbol and be soluble in each other. When I look over here at lead iodide, I can see the iodide over here, and I see that it is soluble in everything. But again, this is the one that has 3 exceptions, which is silver, lead, and mercury 1 here. And I do see that in this particular case, the I is attached to lead, which is part of those exceptions. And because it's an exception, usually iodide is soluble. Because this is the exception, it would be the opposite, which means it would be insoluble. We actually would expect this guy to make a solid. Lastly, here looking at K, which is potassium, which is group 1. It is soluble in everything, no exceptions. That is all I need. I could also look at nitrate if I wanted to. Nitrate is soluble, and no exceptions. Tells me the same thing. So basically in this situation, you would take this guy, which is a solution. You would take this guy, which is a solution, and you would actually get a yellow solid that would actually develop when you mix those two guys together as a result of the lead coming together with the iodide. Any questions on how to use this table? Again, it would be provided to you if you needed it. Okay. So a couple last little things here about solubility. As we talked about, really things do tend to form solutions when they are able to interact with each other in similar ways through those intermolecular forces. Again, that like dissolves like. The solubility of a solute in a solvent depends on temperature. Typically, the higher the temperature, the larger the solubility of a solid in a liquid. You know, something's not dissolving. Sometimes they say heat it up. When you heat it up, you're providing a lot more energy. That's going to allow the solid to kind of come apart and kind of dissolve in the liquid. At lower temperature, we have a larger solubility of a gas in a liquid, and that is because at a lower temperature, if you have a gas, it's going to be moving slower, which means it's going to stay in the liquid part for a much longer period of time before maybe it escapes. And that means it's mixed for a longer period of time and more soluble. Solubility of gases also depends on pressure. The higher the pressure, the larger the solubility. And that's because if you think about Boyle's law relationship, high pressure means small volume. And small volume means that all of our gas molecules are now in a very small location near each other. And just by that process, they're going to be mixing a lot more than if you had a lower pressure, larger volume. Now the gas molecules are spread out and it takes maybe longer for them to kind of come in contact and mix with one another, as opposed obviously in this very small sort of volume. Now, there's other ways we describe solutions. We could describe a solution as being saturated or unsaturated. And if we have a lot of solute in a solvent, that is what is sometimes referred to as a saturated solution. And what a saturated solution means, you pretty much have hit the point where all whatever you were trying to dissolve at that temperature, pretty much you've hit the maximum will dissolve, which means once you hit that saturation point, if you try to dissolve more solid, it won't dissolve. So if you think about like the sugar example, you know, if you had just a glass of water and maybe you took a couple of sugar packets, you know, at the table or whatever, and you dissolved them, it would dissolve. But if you got like the Costco size thing of sugar and you dumped it into that cup of water, at some point you could stir all day, all that sugar is not going to dissolve. So at some point it will just start to pile up. And that's because at some point when you're dumping the sugar in, you've hit the saturation point and no more of it will dissolve. And there's no way to get the rest of it to dissolve at that temperature. So it just sort of piles up. The opposite would be you have hit a unsaturated solution. And an unsaturated solution means you really haven't hit that point yet, which means if you take more solid, it will dissolve. And it will continue to dissolve really until you hit the saturated solution. So if you have like a saturated solution and a unsaturated solution, this guy will continue to dissolve and it will continue to dissolve solid until you hit the saturated solution, and then no more will dissolve. And you'll just start to get, if you continue to try to dissolve, you just get the solid to basically to pile up there on the bottom. A couple of other ways that we can talk about solutions is concentrated and dilute solutions. And when we have a concentrated solution, that means we have a really large amount of solute dissolved in there. If we have a dilute solution, we have a smaller amount of solute. So, you know, if you get like a nice soda drink or something like that from the fountain with some ice, you know, you drink it, it tastes really good, it came fresh from the fountain, you put it in your car, leave it in your car, and you come back later after maybe going to class or something like that, all the ice melts, all that ice now becomes liquid water and now dilutes your soda. You get back in your car a couple hours later, you're thirsty, you go for it, you drink it, you maybe regret it, and it doesn't definitely taste as strong as it did when it came right out of the fountain. It obviously has been diluted, and that happens a lot with chemicals. We usually get chemicals in a very concentrated way, and we do a dilution, which basically means we just add water a lot of times, and we basically dilute it down, and it's not as strong of a solution or a reagent, for example, than it would be in a concentrated form. Any questions on that there? Okay, then we're going to talk next about, we're going to talk next about electrolytes. So let's talk a little bit about electrolytes and sort of what those things are. So electrolytes are substances that, when they go into water, break up into ions. And the other thing that electrolytes can do is, because they do break up into ions, and the ions are really the important part here, it helps sort of complete the circuit, if you will, and it's able to conduct electricity. Was able to kind of conduct electricity pretty well because of the presence of those ions. Now, there's some different types of electrolytes. There are things that are strong electrolytes. And strong electrolytes, when they go for a swim, 100% break apart into ions, which means you no longer have any individual ions by themselves. So if you had something like sodium chloride solution, in sodium chloride, it would basically, solution of sodium chloride, 100% break apart into sodium ions and chloride ions. So 100% of what you would actually have in the solution are actually these individual ions floating around. You would have none of the sodium chloride units still together. So what does that mean? Well, what that means is you just produced a lot of ions really quick. And a very common experiment is they take a light bulb, and let me just draw it as light bulb. And perhaps we have some electrodes hooked up to the light bulb. And if you stuck it into a solution that's a strong electrolyte, like sodium chloride, again, basically you have all these sodium chloride ions floating around. What would happen is this light bulb would go off very brightly. Like, it would be super bright, tons of ions floating around, able to complete the circuit, conduct electricity really, really well. Very bright light bulb. You had something like hydrochloric acid, which is also a strong acid, will 100%, when it goes for a swim, break apart into hydrogen ions and chloride ions. So again, here, 100% of what you would have in the solution are these ions. Again, none of these guys will be in the solution. So if you have that solution, you would have a ton of H pluses, Cl minuses. You would have these ions floating around. Same thing. We hook that light bulb up there. It would also be very, very bright as a result of that. So strong electrolytes 100% break apart into ions. Because they break apart 100% into ions, you have a lot of ions there. Helps complete everything in terms of circuits, electrons really, really well. The result of that is it conducts electricity very, very well. So a strong electrolyte conducts electricity very well. Hence, bright light bulb, basically. Now, another type of electrolyte is one that is known as a weak electrolyte. And a weak electrolyte, unlike a strong electrolyte, will break apart into some ions, but will mainly stay together. So for example, if we took hydrofluoric acid is actually a weak acid, and it's also a weak electrolyte. When it breaks apart, it will break apart into H plus and F minus. Now, different than a strong electrolyte, in this case, we get a few of these ions that are formed, but mainly what we have in solution is actually the HF guys still together. So this is mainly what we have. So what happens if we take a solution of this guy? Again, in this solution, pretty much HF is mainly what we got floating around. But we got a little bit of H plus ions, a little bit of F minus ions floating around. So if we were to hook this up to our light bulb here, because there's still a few ions floating around, it's able to conduct electricity. So it's still able to conduct electricity here. But it can do nowhere near what a strong electrolyte will do. The light bulb will go on, but it will be very dim. So it will light up, but it'll be like, I can barely see anything. You know, it barely lit up, but it still was able to light up, and it's still able to light up because there is still, again, some ions in that solution, which helps it conduct electricity. But again, nowhere near the very bright light bulb that you would see in a strong electrolyte. Now, you may be wondering, they both break apart into ions. You know, how do I know if one perhaps is a strong electrolyte or a weak electrolyte? A couple of big hints here actually can be found with the arrows. We look at our strong electrolytes, it is a one-way arrow, which means everything's going to the product side, and we get pretty much 100% ions here. If we look at the arrow here on our weak electrolyte, it is actually what is referred to as a reversible arrow heading in both directions. There's a forward direction, which goes from reactants to products, and there's a reverse direction, which goes from products back to reactants. And when you see this, this basically means stay together. Little ions over here. It's a bad little. I'm not sure what happened there. Little. Doesn't want to write little apparently, but little about ions there. So a big hint is if you see these arrows, two arrows heading in opposite directions, that's a pretty big hint that it is a weak electrolyte. If you see a one-way arrow where something breaks apart into ions, that's a big hint that it is a strong electrolyte. Any questions on that there? Now, there is one more, which is a non-electrolyte. And a non-electrolyte will dissolve in water, for example. But the key here is it will not produce any ions. And because it will not produce any ions, it does not conduct electricity. So you may be asking, you know, what's an example of that? An example of that would be sugar. You take solid sugar and you dissolve it in some water here, you will get sugar that has basically dissolved. But sugar is basically made up of carbons, hydrogens, and oxygen, as we saw earlier. And those are all nonmetals, which means these guys are going to be covalently bonded, going to be sharing electrons, no transfer of electrons. And since there's no transfer of electrons, there are no ions that are present. So because there's no ions, if we took our kind of light bulb and we put it into a sugar solution, it would not go off. So it stays off. It doesn't conduct electricity, again, because there are no ions in there. So no ions, no conducting. Question on that. Water, for example, pure water is a bad conductor of electricity because it doesn't have any ions present. Now, let me be very clear, the water that comes out of your shower and so forth is not pure water. They actually put ions in it, which means it does conduct electricity really well. So do not, blow dry your hair in the shower because you will get fried. But, if you have just really pure H2O, nothing else in it, it's actually a bad conductor of electricity because, again, it doesn't have ions that are present. And one more safety, again, water coming out of the sink and so forth, not pure water, and will conduct electricity. So here's a much prettier picture of my light bulb example. So here we see sodium chloride, which is a strong electrolyte. So again, in solution, 100% breaks apart into sodium ions and chloride ions. And again, 100% of what you got going on is there. As you can see in this picture, conducts electricity really well. It goes off very brightly. Here's HF, which is our weak electrolyte, which again can be seen by these reversible arrows. Does still break apart into a little bit of ions that are happening there. But mainly this is what we have going on in that solution. As you can see here, mainly the whole thing still together, but a couple of ions or so floating around, still able to conduct a little bit of electricity. And as you can see, again, light bulb does turn on, but it is dim. And down here is sugar, which again goes from solid to being dissolved, but no ions present. And again, we see that the light bulb does not go off in this particular case. So sort of a cliff note way of recognizing, if you're looking at equations, which one is which. Again, what you would want to look at in terms of the top guy, I see a one-way arrow and I see ions. That probably is going to be strong. I see two-way arrow and I still see ions. That's going to be probably weak. I see sugar on one side and same thing on the other side. That's going to be probably your non-electrolyte. So if you look at an equation, you got the same thing on both sides of the arrow, probably non-electrolyte, and there's no ions on either side. If you have a two-headed arrow, that should probably be a weak electrolyte. A one-way arrow to ions should be a strong electrolyte. So that's, again, a way you could kind of hone in on which one is which.